who's going to talk about subconvex equidistribution of cusp form. Oh my God. Sorry.
Thanks very much. Okay, so I'll copy the title up here. Okay, so this talk I'll start a bit generally, as many talks on the subject do, by phrasing a question about Riemannian manifolds. So in such a manifold, you can take a sequence of eigenfunctions. So we'll take square integrable eigenfunctions, and we'll write the eigenvalue as lambda. So they'll satisfy some equation of this shape. And the general problem that is far beyond the scope of this talk will address kind of an offshoot of a special case of this problem is how does phi behave as lambda tends to infinity. And more specifically in practice, how does the behavior interact with the classical dynamics of the geodesic flow on the manifold? So the key word here is behave. You have your choice of how you want to quantify this. One nice way is in terms of what's called the L2 mass, mu phi. So this is a probability measure on M given by the following formula. So for all test functions on the manifold, one defines a measure by the values it takes on functions, and they're given by inner products of this shape. So it's a measure that quantifies where phi is distributed on the manifold M. And so the basic question is, how do these look as measures as lambda tends to infinity? And I'll just say that we know the most about this question when the manifold is something arithmetic, like the modular curve, and when the eigenfunctions are assumed also to be Hecke eigenfunctions. So I'll write the Hecke eigenvalue like this. So Tn are the Hecke operators. So the theorem that'll be the point of departure for the talk today is what's called the, I'll write it big, the AQUE theorem. Which is some synthesis of works of Lindenstrauss and Sander-Erigen. Which says that under the above assumptions, so in other words, in that case, you take any fixed test function on your manifold, in this case SL2Z comod H, one has that this measure tends towards the uniform measure, which I'll denote by mu, This is the measure given by integrating against the constant function, normalized. Okay, so I'm kind of doing so I hope the statement is clear that we have a convergence of measures in a weak sense, so tested against these functions. There are a few remarks in order here. So one is that this answered a conjecture of Rudnick and Sarnak from '94. One can also say that so this conjecture actually is more general. One can drop the A. One can also drop the U. So it refines a QUE theorem by many people. So Schneermann, Colin de Verdier, and Zeldich in the 70s and 80s, which gave a weaker assertion for almost all eigenfunctions. And there are plenty of interesting questions that one can and does ask about the problem in greater generality, but for the purpose of today's talk, everything will be starting with this AQUE theorem. Absolutely, yeah. So I mentioned that offhandedly that they made a more general conjecture, which we don't have too much time to get into today. So we have this theorem, and it raises the natural question, which has been around since the 90s. So at what rate does this convergence happen in the context of the AQUE theorem? So to make that discussion precise, we can introduce just a little bit of terminology. So let's say we're given a function, we'll call it epsilon, from the set of all phi as above to the positive reals. Let's just say that mu phi tends to mu at rate epsilon. If so, I'll state the conclusion of the theorem in a quantitative form that depends upon epsilon. So for all smooth functions on M, there exists some constant so that for all phi as above, so maybe more precisely in the AQUE theorem, one has an estimate like so. So up to some constant that depends upon the function we test against, we'll ask that these measures become equal at some rate epsilon of phi, just as a matter of terminology. So in practice, one assumes that epsilon tends to 0 as a function of the parameters of phi. So this terminology will give us an efficient way to describe what is known here and what is expected. Okay, so the strongest thing to expect in this setting is what I'll call the optimal AQUE conjecture. So this asserts that under the running assumptions of the theorem we stated, that one has this convergence of mu phi to mu at rate basically lambda to the negative quarter. So if you take any exponent, eta positive, you can let that be the rate at which this convergence occurs. Where here lambda, as on the board I just erased, is the eigenvalue of phi. And I'll attribute this conjecture to, so Sarnak in 93 and Luo Sarnak in 94 and Watson in 2002. So they gave very strong evidence for this conjecture by, say, verifying average forms of it. So it holds in some sense on average over all phi. And later showing that actually it follows from GRH in the form that I've stated in here. So of course there's a weakening of this conjecture that one can demand that I'll call the strong AQUE conjecture. Which doesn't need any additional attribution because it'll be a consequence. It just says that one can take epsilon of phi to be lambda to the negative delta. So here I hope the notation is clear that delta is some positive constant that doesn't depend upon phi. So these are a couple of conjectures that have been around, as indicated, since the early to mid-90s. And I think it's fair to say they've received a fair bit of attention, but there hasn't really been any progress or maybe sign of hope that one could ever prove something like this in the near future. And I should remark that in the AQUE theorem, as stated above, so the proof uses ergodic theory and measure classification. And so it gives no rate, or an ineffective rate, one might say. So both of these are natural questions that have been open for quite a while. So in the past couple of years, there's finally been maybe some glimmer of hope that one can possibly attack this question. And that's what I'll talk about today. So the aim is to prove a level aspect, in fact, prime level aspect, analog of this strong conjecture. And I'll state a bit more precisely what I mean about this in a second. Now, before getting into the new results for today, I want to recall just a couple other things that we actually do know to give kind of a more full picture of what methods we have for understanding these questions. So one result is due to Sarnak around 01, followed by Liu Ye and Lao Liu Ye. So they showed that this strong conjecture holds in the affirmative if phi is a dihedral form. So a dihedral form being one that comes from some quadratic extension of Q by a theta lift. So this is kind of a very, very special case of the problem. It's a very thin case in a quantitative sense. And the argument doesn't really allow one to make much progress on the general case, as we understand. So there's also a result of Holloways and sound. It was published in 2010, which can be stated most simply as an analog of the theorem I started the talk with, the AQUE theorem. So in the weight k going to infinity aspect. And moreover, it's worth recording, they do get an effective rate of something like a logarithm power inverted, where k is the weight of phi. And so the three results I've mentioned, this AQUE theorem of Lindenstrauss and sound, this dihedral case, and the Holloways sound theorem I've mentioned here, represent basically the three methods that until recently we had to prove anything even qualitative in this setup. So the variant of the problem in the level aspect was also treated by myself first in 2011. So first in the square-free level aspect, which is the one that's, it turns out, most important for today's talk. So the way one sets up the problem there is one still takes phi, say, to be a weight k holomorphic cuspidal new form on gamma naught of n. Let's say n is square free. And as above, one can attach a measure mu phi, but it's best to define it as a measure on not the varying quotient involving gamma naught of n, but instead this fixed quotient, h mod SL2z. And one defines it by the same formula as before. So if we have a test function that I've tended to call psi, then the value of the measure on psi is again given by this inner product. And here it's worth noting that we're kind of identifying psi in this inner product with its pullback to the level n modular curve. So here we have this big quotient upstairs mapping down to a smaller quotient. And so we have functions phi on the big quotient. We can always pull psi back up to this big quotient as well. So this diagram here gives meaning to the inner products I've written on the right-hand side. So the theorem obtained by myself in 2011 was that mu phi again goes to mu, and here with rate, as in the Hollowinsky sound theorem. So logarithmic in the parameters of the forms. And so the proof used the Hollowinsky sound method. And I think it's fair to say that from the perspective of this method, as well as any others that we knew, the problem here seemed about equal in difficulty to the conjectures that I started the talk with. Phi is a hecaform, yeah. Okay. Okay, so the theorem that I'll state now so I'll state it as an expected theorem for reasons that I'll explain in a second. And I'll call it theorem MN because it'll essentially be a literal concatenation of a result of Munshi that was so announced a couple of years ago and kind of in the final stages of being written up now, and myself from recently. Which says that the following: fix a weight k, an even natural number. Let phi go through a sequence of new forms on, let's say, h mod gamma naught of p, where p is a prime tending to infinity, and we take phi to be of weight k. So then the conclusion of the theorem is that, well, there's one numerical parameter that's varying this prime p. And so the conclusion is that mu phi tends to mu at rate some p to the negative delta for some positive exponent delta. And just to remind you what this means when we spell out the definition, so that is to say for all test functions on SL2Z, if we form the inner products as before, we can bound this by some constant depending upon psi divided by a positive power of the prime p. Okay. Any questions so far? So I'll say that the theorem does not seem to cover it at the moment, but I'll explain why more precisely in about 10 minutes. This is p to the delta. Yeah. Otherwise, we wouldn't need to finish the talk, I guess. Thanks. Wait, is that any better? Gosh. Well, got to emphasize the delta. OK. All right, thank you. All right, so in the course of explaining the proof, I'll recall kind of the standard way one analyzes this question and also how one figures out what the optimal rate should be. And this is largely due to Sarnak, Luo-Sarnak, Watson, and others from the 90s, the analysis I'm about to present. So the rest of the talk will be about, well, first how we reduce this to a subconvexity problem in a completely standard way, and then how we address that problem. So first, let's recall the spectral theorem for SL2Z. So it says that you can compute inner products of functions on H mod SL2Z by estimating separately the contributions of cusp forms and Eisenstein series. And the Eisenstein spectrum consists of constant functions together with integrals of Eisenstein series. And moreover, any f, let's say in CC infinity of this space that I'll call M, has a rapidly convergent spectral decomposition. So that spectral decomposition might look something like f is inner product with the constant function times 1. Maybe for now, to avoid writing I'll assume this is an L2 normalized, or a normalized inner product, plus something like a sum over psi in a basis for the space of cusp forms of f psi, plus dot, 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 where dot, dot, dot denotes the contribution from the Eisenstein series appearing on the right. And so the conclusion, so since, yeah, orthonormal basis. Thanks. So since, I guess when you take the constant function, it's normalized to be a probability measure. And since the ordinary, the uniform measure vanishes for all psi cuspidal and or Eisenstein, this is a standard reaction that it suffices to show for such psi, meaning psi that are cuspidal or Eisenstein, that mu phi of psi is bounded by p to the negative delta, where we allow the implied constant to depend upon psi. And maybe finessing a small detail, we should require the dependence to be reasonable as t varies. So polynomial would suffice, or even probably measurable. Yeah.
The first case of the strong Q conjecture in any aspect, I guess.
Yeah, outside dihedral cases. Yeah. Sorry, could you repeat the question now that I've... Yeah, a very small real positive number. Exactly, yeah. Yeah, delta, the convention is it's just a very small, there exists a delta. Yeah. Well, I mean, maybe I should just emphasize, I mean, there's a little t in the theorem, so I'll explain why in a second. Well, okay, and I think the proof is actually, the structure of the proof is kind of surprising and interesting too, so. Yeah. Yeah, so there's this annoyance that, so I'm sticking to square-free levels in this talk because of basically a lack of vocabulary on the part of analytic number theorists to properly formulate in a concise manner which vectors one should choose in level aspects that are not square-free. So new forms we can, of course, refer to in a public talk without having to define, but kind of new forms are not the right vector to choose for powerful aspects. So maybe the way to kind of reconcile the two questions is the first QUE type result of this shape that does not follow from local means by, say, choosing the wrong vectors. So it's the first one that actually gives a subconvex estimate. Maybe that's the... I hope I didn't confuse everyone. No, that doesn't show up. Yeah. 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 So. I mean, I have a paper actually recently where I give a candidate vector that fixes this issue in the depth aspect. So if you look at my paper on microlocal lifts p-adically, that addresses this, how to make a tighter equivalence between the QUE question and the subconvexity question. Yeah. Okay, so we want to show this estimate that I've written here for psi of a specific form. And there's a known formula for this. So it's a formula due to Watson in 2002, building on work of Harris and Kudla in 91, and then kind of finessed for the level aspect by myself in 2011, and many more people like Yuki who have refined this kind of stuff quite a bit, which says that under the conditions I've written down on the right-hand side, this squared period is given by, well, an L function so this is some degree 8 Euler product, which it would do us no service to define, divided by an analytic conductor. And I'll put in this analytic conductor exponent a little o of 1, where the meaning of little o of 1 is just something that tends to 0 for psi fixed, and let's say the parameters of phi tending to infinity. The L function is known in this case to be non-negative valued. No, we should. So I mean, in fact, so okay, I guess this formula proves it, but yeah. And just for the sake of expediency, I'll introduce the definition. I'll call this right-hand side L over c to the quarter plus little o of 1. Okay. So this is all still like a very standard direction. Theorem Mn reduces to the following estimate that I'll call star, which says that L over c to the quarter is bounded by well, the same c raised to the negative delta times, let's allow some polynomial dependence on the conductor of psi, maybe to the 1,000 or something like that. So this is for some delta greater than 0 and maybe a greater than 1,000,000. Just and so, I mean, those of you who know, this is the setup of the subconvexity problem. So we're going to address this by proving a subconvex bound in this case. And it's worth also noting that in this case, so this number I've defined to be c up here happens to be roughly of size p to the 4th, at least for fixed values of psi. So saving a power of c is the same as saving a power of p. I guess I'll leave the theorem stated in the middle for now. Okay. Now let's do kind of a very tautological further reduction. So I called this estimate asterisk. And so clearly theorem mn follows from asterisk. Let's divide asterisk into two cases. Let's call one case case A and one case case B, where A is the case of asterisk in which the kind of fixed function psi is an Eisenstein series. Let's call assertion B the case where psi is a cusp form. So those are, of course, the two possibilities. So if we can treat both of those, then we have the theorem. So then the structure of the proof has a very kind of interesting form. So on the one hand, I'll put it on the same board. So this will also explain the division of the credited theorem. So theorem M, I'll state as the assertion that A holds. And then theorem N, with the credits and the names kind of in the obvious parallel sense up there. So you'd expect it to say that B holds, but I mean, to be kind of a bit more honest, what it actually shows is that A implies B. And then the two of them together, of course, imply what I've called theorem Mn. So for emphasis, this is Munshi, and this is myself. So I want to spend the rest of the talk kind of explaining the proof of what I've called theorem N here, like why in the world there should be any implication between two results of this shape. Which I don't think there's any pre-existing intuition or kind of model result on which to base an implication like this. I mean, for most purposes, the contributions of these two parts of the spectrum don't really see each other. But for here, I mean, I should say, I mean, the preprint is still being finalized, so we should. Well, I mean, and it is being finalized. We talked about it, Munshi and I, quite a bit while he was here. This preprint is at least available and submitted, so that's what I'll talk about for the remainder of the lecture. And maybe it's worth noting that in this theorem, what I've called theorem A, the case where psi is Eisenstein, there's a factorization of the L function into Euler factors of degree at most 3. And so that's the actual problem he addresses. And it seems pretty clear that the technique does not apply to the higher degree L function that comes up in part B. That's an interesting question. So at present, my result seems to require square free level without further work. So it'll require something really non-trivial to do any other aspect. Maybe ask me at the end of the talk again, and I'll say a bit more of it. Munchi's result, it's not quite clear to me. I again imagine square free level would be no issue, but there's a very, very bizarre restriction in the method at the moment to essentially prime level. So let's talk about the proof of theorem N. So let's remember what we started with. We wanted to bound L over c to the quarter plus little o of 1. So we can take a step back for a second and remember where this came from. This came from basically the inner product of phi against psi phi. Let's suppose here that phi is L2 normalized now. And this all squared. So the way I got into this problem came from some work I've been doing over the past 7 or so years, where I've been studying expressions that are bilinear in phi by using something called the Shimizu theta lift, which basically expresses phi of z1 times phi of z2 as an integral that I don't have time to explain in detail, but it'll be an integral of, say, phi of w against some complicated theta function, depending upon all three variables. And it turns out that if one plugs in a sufficiently precise form of this identity into this inner product, one gets an expression of the following shape, where I'll define everything on the next board. So I'll call it phi theta sharp, h sharp, squared. And so the first step in the proof is we're going to study this ratio of L functions, or equivalently this period, by means of this particular integral representation. And I'll mention, in fact, so actually in the article, there's a lemma of Yanan Chu that he proved en route to some other results on cytochorolifts, together with some local calculations that I worked out that kind of give this error directly. In any event, I mean, his proof actually goes through the same set of implications. So the first step is to kind of linearize the problem with respect to phi using the Shimizu lift, and then zoom in on that lower item. No, I haven't told you what anything is in that inner product, and that'll come in a second. So imagine that I wrote where ... on the bottom. Yeah, phi is L2 norm 1, as in the upper right. So phi, okay, yeah, so let me put some dots here and say this, I mean, this will be off by something like the difference between the arithmetic and analytic normalizations of phi. So there will be factors like L of add phi 1 floating around in there. Okay. So we reduce to showing the following, that this inner product phi theta sharp h sharp is bounded by p to the negative delta. Now here, let me spell out everything. So theta will just be the usual Jacobi theta with a y to the quarter in front. Theta sharp, I just need a quick way to write theta of pz. Just some notation. So I'm going to define h before h sharp. H will be something like the inverse Mas Shintani, or inverse Shimura, or Mas Shintani Walsperger lift of psi. So it'll be written in the following form. So this is something like, I don't know the best way to say it, but it's something like an inverse Shimura lift of psi. And then finally, I can define H sharp. So H sharp is what you get by putting a P in the argument there. Yeah, I'll write it on the next board. So somehow, so H sharp is a half integral weight form on gamma naught of 4p. And it's worth emphasizing that all of these h's depend upon psi. That's where it enters into the discussion. And there's a useful fact, which is that it turns out that H sharp has the same L2 norm as H, which is not entirely obvious, but plays a useful role. So in this inner product I've written down here, all three of the forms are effectively unit vectors. And the fact that you can actually position yourself, you can find an integral representation where all three of them are unit vectors, and they satisfy some other nice conditions, like one of them is unramified. This is kind of specific to the square free level aspect. And represents one of the obstructions to kind of generalizing this method a bit further. Okay, so we've arrived at this problem of bounding this inner product by a small power of p to the negative delta. So now there's a technique called the amplification method. So due to various people, Ivanic Sarnak, Duke Friedlander Ivanic, Venkatesh, Michelle Venkatesh, in the 90s and early 2000s. So what I called star will follow from might as well add a third star, where triple star will be the assertion that if we take phi multiplied by theta sharp, and then we take the L2 norm, then we can produce an asymptotic formula for this L2 norm. Plus some very small error. And I'll say informally, with a bit of room. So in the last few minutes of my talk, I'll explain how to actually prove triple star, which is really the meat of the whole argument. But before I do that, I want to say just a couple more words to kind of give you an indication of why it's plausible that triple star should be sufficient. So what we really need is, so we're going to use half integral weight Heck operators. So for small l that are squares, maybe L is of size p to the alpha, where alpha is small and positive. What we really want is to show that if we apply a Heck operator to phi theta sharp, then we get 1 over the degree of that Heck operator, which is something like L, times the corresponding inner products on the right-hand side. Plus an error that is like small in p and maybe polynomial in L. So p to the negative delta, L to the a. So the meaning of a bit of room to spare is that when we write down the proof of triple star, it'll kind of be very obvious from every step that the proof more generally extends to give what I've written on the lower blackboard with this L parameter. And so the amplification method is all about taking a statement like this and using it to buy a little bit in the main term. So the idea is that if star fails, then the Cauchy-Schwarz identity, phi, theta sharp, h sharp, so this being bounded by, say, phi theta sharp squared. So this is nearly sharp. And so morally speaking, phi theta sharp is kind of nearly a multiple of h sharp. Which can be seen to contradict what I've written here, say triple star subscript L. The reason we get a contradiction here is because, so typically TL H sharp is something like, well, lambda phi of H sharp root L. This is typically about 1 times H sharp. But you can check that if you apply TL to phi and take its inner product and do the same thing with theta sharp, this side here is bounded by L to the 3/4. This side here is bounded by, say, L to the quarter plus 7/64, which is in particular bounded by L to the 3/4 minus beta. So this is bounded by L to the 3/2 minus beta, which I can write as 1/2 minus beta times the degree of TL, which is contrary to the asymptotic relation that I've written down here. So the remaining question that I'll address in the last few minutes of the talk is, how do we actually establish triple star? So we're going to use the spectral theorem on L2 of H mod SL2Z. So this inner product, we can expand like this. And for the purpose of discussing the proof, it'll be helpful to introduce the following notation. Phi lower sharp of Z will be phi of Z over P. We can rewrite this as, say, phi lower sharp squared theta squared. And then we can spectrally expand this. So we'll get the contribution of the constant term plus some error term. So we'll note that the constant term gives us what we wanted on the right-hand side. So this term here is just the product of these L2 norms. And the error term will be a sum over, say, cuspidal psi of the inner products of psi with the two things we've written above. Plus, finally, an integral over Eisenstein series analogously. But you'll note here that this expression is basically what Munchi's theorem addresses. This is bounded by, say, something like p to the negative delta by theorem M. Because theorem M says that we have QUE for phi when we test it against the Eisenstein series. This expression here is bounded by, say, t to the negative 1,000 for t away from 0. So the only question is to address what happens with this top expression. And we should note that we'd be in big trouble studying this top expansion if we had, say, what I've called lowercase psi, if we consider the contribution from when this is actually equal to uppercase psi. Because somehow the problem that we wanted to understand at the beginning of the talk enters as a subproblem here. But then it turns out, as I noted in some unrelated work about a year ago, that this inner product is equal to 0 identically, kind of surprisingly. And so, what's that?
Do you use anything about the level being prime, or like where does that?
That entered in the very first step when we got an inner product formula that kind of on the nose nearly recovered the convexity bound. Yeah. So this is a cute fact that I could explain in 2 minutes, but I think I'd rather just stop for questions, if any, and end the talk here. So, thanks. Yeah, so theorem N, the one that I proved and talked about, kind of holds in as much generality as you could want. So take a number field, take a cuspidal automorphic representation, and in the prime level aspect, you get something like this. So Moss forms are no issue. In Munchi's work currently, he assumes it's a holomorphic form. But I don't know if that's for convenience or essential. If psi is a cusp form, then it's orthogonal to the squared magnitude of the Jacobi theta function, which is basically an Eisenstein series. So that's, yeah, I mean, you can rephrase it as saying that this is basically an Eisenstein series.